Okay, let's take a look at reaction mechanisms. That's the actual procedure, the details, oftentimes a series of steps by which a reaction occurs. For example, if we're decomposing dinitrogen pentoxide, it's going to turn into nitrogen dioxide by oxygen. But if you study it, you'll see that there's some intermediates that are formed that are then consumed. Here's the results of this study.
The decomposition of dinitrogen pentoxide is believed to follow a three-step mechanism. Step 1 is a fast equilibrium.
Notice they're giving you the step.
Step 2 is the slow rate-limiting step.
There's step 2.
Step 3 is another fast step.
And there's step 3. Now, if you'd actually written each of those down, you'll get step 1, step 2, and step 3. Let's mention them very briefly. So first it decomposes to nitrogen dioxide, fine, but also some nitrogen trioxide, which isn't even shown here. That nitrogen trioxide then reacts with what it broke into to give you nitrogen monoxide, once again not even part of the overall formula. Some oxygen, aha, that showed up, and some more nitrogen dioxide, which is part of the products. So two of these things don't even, show up in the overall reaction, and then that intermediate reacts with the other intermediate to generate yet again some more NO2. What a fascinating mechanism. Who would have guessed that's what actually occurs? Notice that two of the steps are fast and one of them are slow. What we can conclude is that the reaction can't go faster than the slow step. This is the rate determining step. The analogy I always come back to is a highway that's 5 lanes for a half mile, and then somebody had a bridge that had to narrow things down to 2 lane. This is no better, and perhaps worse, than a 2-lane highway, since it bottlenecks at that point. Think of a slow step perhaps as a bottleneck. Also, we can conclude that nitrogen trioxide and nitrogen monoxide are in fact intermediates, since they show up nowhere in the overall chemical reaction. There are cases where you could also have a catalyst, and we'll deal with them in a separate case. So those are the things that we can conclude. Overall, here's what we can say about reaction mechanisms. The sum of those steps better add up nicely to give the overall reaction, and if you added up each of the 3 steps for dinitrogen pentoxide, you would have gotten exactly that. The mechanism must agree with the experimentally determined rate law. It's supposed to be what really happened. You can't just make stuff up. And the reaction is only as fast as its slowest step, which we pointed out. Now here's an important thing that really shows up when people ask the tough sorts of problems. The rate determining slow step determines the rate law and the molecularity of the overall reaction. That's a case where you can see if it's first order, those coefficients do become exponents. So the rate does determine the rate law and the molecularity of the overall reaction. However, if those things in that rate determining step if the reactants are not the same reactants from the chemical reaction, you might have to do some substitution, since you can't say that it's equal to a concentration of a certain thing that isn't even a starting material. Let's see examples of that. Okay, here's a standard type of chemical reaction. We are reacting nitrogen dioxide with fluorine. The mechanism has a slow step. We could say that the rate is equal to K times the concentration of that. There's no coefficient, times the concentration of that. That's fine. Are those both reactants? They are, so we're done. That is the rate law. First order with respect to nitrogen dioxide, first order with respect to fluorine, you're done. Here's another one, a simple form of it. A plus 2B turns into C, and it's a 2-step reaction mechanism. There's the slow step, aha. So can we simply say that the rate law is equal to concentration of D times B? Well, it's true, but it's not useful because D's not a reactant, so you can't double the concentration of D if you're not adding any. However, we can mathematically say that D came from A and B. So D is equal to A and B. We substitute in, and we say it's first order for A and second order with B. I honestly don't know at this point if this shows up on AP chemistry tests. It might be beyond the scope of it. I'll have to ask around. But you can see how it's fairly elementary to just substitute in and then solve for it. So this is a little bit about rate law from reaction mechanisms.